Hello everyone, my name is Satvik Sahu and today I'll be presenting my MS thesis work on task conditioned energy based world models for latent predictive control. Here's a brief overview of what I'll be presenting today. First, I'll introduce you to the main topic of my thesis, robot learning, and I'll give the motivation behind it. Then we'll look at some of the methods in the literature in this field, then some of the challenges that are faced by existing methods in this field and the setup to my MS thesis. Next, we'll look at some of the methodology employed in my MS thesis, and then I'll tell you about the results obtained from the experiments conducted during my MS work, and finally I'll conclude with the conclusion and some future directions to this work. So, what is robot learning? Robot learning aims to develop models through which robots can perform any task desired by human beings. But the main question that remains to be answered in this field is, how do machines learn and think? And are the current learning frameworks that we have enough? Is a simple mapping from sensor inputs to action outputs enough? Or recently there has been a boom in robotics, where you can see robots of many different shapes and sizes and embodiments being deployed everywhere. You might have seen many different demonstrations of very incredible robots, but household adoption is very rare. This is a phenomenon known as the Moravec's paradox, where easy tasks for humans are actually very difficult for robots, and tasks that humans consider very difficult is actually easy for robots. Now, you might have seen incredible demos from SOTA robot models like Pi, which is physical intelligence, and OpenVLA. They look so promising, but household adoption is still very rare. That is because transparency builds trust, and currently the models that are there are not transparent. Their thoughts are like a black box. So perhaps the next wave in AI will be led by models that humans can actually trust. But who cares about robots? Maybe a researcher who needs to focus on their work, not daily chores, or a firefighter or disaster relief worker with many lives resting on their shoulders, or perhaps an elderly couple that needs help with their daily tasks. Current robot learning paradigms are heavily influenced by sequence modeling methods, where you have action chunking with transformers, which produces chunks of action sequences at a time, diffusion policy and flow matching policy, which work on the same principle as image generation models, but just instead of images they generate robot actions. Then you have models which have open world understanding with VLA. VLA is vision language action models. These just work like ChatGPT, where you can input some kind of task into the model and the robot is going to do it for you, but just instead of text like ChatGPT does, the models output action sequences instead of sequences of words. Then another very new and upcoming paradigm in robot learning is latent model predictive control, where you have a model which has learned some kind of internal simulation of the world, and it has a cost function, and it can assign, using this cost function, a particular cost to an action sequence based on a desired task to be performed. And these models iteratively optimize the action sequences using the internal learned simulation to optimize the actions to perform the desired task before actually performing them in the real world. Now, the real world is messy and unstructured and has a lot of stochasticity. Can we probabilistically model these environment dynamics? One might start out by looking at a probabilistic view of this kind of modeling, where you start out by trying to learn probability of a particular continuation to a set of past observations x, the continuation being y, and this probability is conditioned on the task at hand, which is z. But modeling this as a Boltzmann distribution has drawback, which is that the denominator on the right side, which is also called the partition function, is an intractable integral, because the set of possible continuations to a given sequence of past observations is very, very huge, and you can't really integrate over it. So we can shift our view into a energy based view of this probabilistic modeling, where you only learn an energy function between a particular set of past observations, a sequence of possible continuations, and the particular task at hand. Now, since there are many possible correct continuations to any set of past observations, the distribution that comes up for the continuations y is multimodal. For example, if we look at the distribution given by the dotted line, it has 3 modes. For example, think of this as a robot which has 3 different cubes in front of it, and it has to pick up one of them. Each of these modes correspond to continuations from the current observation corresponding to picking up one of these 3 cubes. By conditioning your probabilistic model on task 1 by z1, you can actually assign more of the probability to, say, the first mode, which will be to pick up the first cube, and you will have a probability distribution something like this, and sampling from this distribution you would get possible actions which will actually pick up your first cube. And similarly for task 2, where you can then pick up the other cube by conditioning on a different action. Now let's get back to what is model predictive control in the latent space. Now, in model predictive control, you have a model, and this learns the dynamics of the environment. How it does it in a predictive manner, where given some particular latent representation of an observation et, which is a vector, and a particular action being performed at time t at, which is also a vector, you learn a predictor function which can predict the latent representation of the next state would be if action at was performed at state et. And then you can assign a cost to a particular sequence of actions, a from time t to time t plus capital T, by this cost function c, which is conditioned on the representation of the goal state. And by optimizing your action sequences to minimize this cost of actions given this particular goal, you can find the optimal action sequence that should be performed at this particular time. During deployment in the real world, it is difficult to estimate this cost function because the latent representation of the goal is unknown, because we have not yet performed the desired action, so we don't know where we are going to reach in the future when we successfully complete this action. So the current major challenges in robot learning are that these VLA models are very costly to train because they have several billions of parameters. Current models spend the same amount of thinking for simple as well as complex tasks, which is not very much in line with how humans would think. Energy-based models are currently trained with contrastive learning paradigms, where you have a positive example and a negative example. So the number of samples required to train this kind of models would be at least 2 times more than those trained with non-contrastive. And finally, the cost function for this MPC, which is dependent on the goal latent, is not feasible because this goal latent is not available during inference time in the real world. So what if we combine the best of whatever we have, which is the open world understanding of foundation models, the adaptiveness and inference speed of latent MPCs, a non-contrastively trained task conditioned energy based model as to estimate the cost function for the MPC, we would get task conditioned energy based models for latent predictive control. Coming to the methodology, here is how latent predictive energy based world model works. First, you have a visual observation at time t, which is OT. This OT is an image, and you pass this image through the latent encoder G theta, which is based on the vision transformer architecture, to obtain a latent representation of this image observation at time t called ET. This is a vector. Now, passing this ET vector through a predictor model H theta conditioned on a representation of the given task at hand Z, you can actually predict the representation of the state at time t plus 1, which is the next step. We call this E hat t plus 1. At the same time, you take the actual visual observation at the next step and pass it through the latent encoder G theta to obtain the actual latent next state ET plus 1, and calculating the error between the predicted next state representation and the actual next state representation gives you the energy. This energy corresponds to the energy that OT plus 1 is the correct continuation of OT given the task Z. In the meanwhile, to prevent the model from mapping all images to the same vector, we employ a regularization technique by storing all of the visual observations we encounter into a buffer B. And at each training step, we sample a batch of visual observations BO from this buffer B, and we pass them through the latent encoder G theta again to obtain a set of latent state representations and apply a sig-reg regularization loss on these latent state representations to prevent latent collapse. What is sig-reg regularization? The full form is sketched isotropic Gaussian regularization. The goal of this regularization is to match the latent space distribution to the d-dimensional standard Gaussian distribution, where d is the dimensionality of the latent space of your encoder. Now, to do this, you first sample latent vectors Zi from your latent encoder G theta, just like we were doing before. Then you sample a random direction on the d-dimensional unit sphere and project all of these latent vectors onto that random direction to obtain scalar projections Si. And the loss is calculated as the value of a statistical test comparing the distribution of all of these projections with the one-dimensional standard normal distribution. And this regularization is based on the Kramer-Wold theorem, which states that if the distribution of all 1D projections in all directions are standard normal distributed, then the full space is an isotropic Gaussian distribution. Now, inside the EVM, what we actually have is a joint embedding predictive architecture, or a JEPA. That is because we jointly embed the current visual observation and the next state visual observation using the latent encoder, and we have a predictive model that is trying to predict the next state latent representation using the current state's latent representation. This is a non-contrastive training because we have not sampled any negative examples. We are only training from the positive examples, that is the correct next state visual observations. And we have a SIGREG regularization that is preventing latent space collapse, which is that it does not allow the latent encoder g theta to only map all of the visual observations to a single vector, in which case it can actually minimize its prediction loss, which is the energy that we talked about. Now, to train this model, what we do is we have a loss function which we need to minimize by optimizing our model parameters theta, where you have your E of the energy function on the current visual observation, the next steps visual observation, and the representation of the task at hand, which we had already seen was the error between the predicted next state latent representation and the actual next state latent representation, which is expanded here. Then we also add to this predictive loss the SIGREG regularization loss multiplied by a hyperparameter which is lambda. Now, to make the model actually think in the latent space, what we do is called a latent predictive rollout, where we start with the current visual observation and encode it using g theta to get a latent representation ET. Similarly, we encode the current task tau using a task encoder g theta to obtain the task representation z. Then we condition the predictor h theta on z and predict the next state latent representation e hat t plus 1, and iteratively go on predicting the next states in an autoregressive fashion using the predictive model h theta to obtain a rollout of k future latent state representations from e hat t plus 1 all up to e hat t plus k, where k is your horizon. In this way, the latent predictive model can perform imagination in the latent space. Now, how do we use this to resolve our issue where you can't really have a cost function for MPCs during inference? So you can start with a latent representation ET and a task tau, and we want to assign a cost to a sequence of actions A from A at time t plus 1 to t plus k. So we perform our latent rollout as seen before, as usual, to get a sequence of latent representation E hat t plus 1 to t plus k as shown before. Then we perform a rollout using the action sequence at plus 1 to at plus k on the pre-trained latent MPC, which we saw before, like TDMPC or live-world model, to obtain another sequence of latent representations E tilde t plus 1 to t plus k. Now, the cost can be calculated as the mean Euclidean distance in the latent space between each corresponding latent rollout vector, as seen in this formula. Okay, so now our model can actually perform imagination in the latent space, but we as humans cannot really think in a very high d-dimensional space. So how do we comprehend what the model is actually thinking? For this, we trained a convolutional decoder model, T gamma, which takes the encoding of a visual observation OT and decodes it back into an image by trying to reconstruct the image to O hat T. And the data set I used for training my model had 3 cubes in front of a robot arm, where the task was to pick up one of the cubes as a text instruction. For example, pick up the red cube, which you can see in the image. Now these are some of the results in our successful training run. After successfully training the model, we use the latent decoder D gamma to actually see what the model is imagining based on a start latent representation by conditioning on two different tasks, Z1 and Z2. And this is what it looks like. So this is the original video of the robot performing an action. The correct task was pick up the green cube. We can see that the reconstructions are pretty accurate in terms of the motion of the robot. So we can conclude that the latent space has enough capacity to encode all the information about the robot's motion and the environment. Here we have the decoding of the latent imagination given the correct task, that is lift the green cube, and we can see that this action, the robot's actions here actually match what the robot is doing in the original ground truth video. So we can say that yes, the model is correctly comprehending the task given to it. And here we have the decoding of latent imaginative rollout with the wrong task, which is lift the red cube, and we can see that it is actually going and lifting the wrong cube because it was given in the wrong task. Now we compare the energies assigned to the wrong sequence of actions and the right sequence of actions this time. So in last semester, because I was not using the Sigreg regularization laws, the latent space had collapsed and all visual observations were being mapped to a very small region in the latent space. That is why there is not much difference between the energies assigned to the wrong sequence of latent observations versus the right sequence of latent observations. But here, as you can see, for the correct task, the energy of the model did not go very high, whereas for the incorrect task, the energy of the model has actually gone very high, and there is a substantial energy difference between wrong task and the right task latent representation sequences. Here is dimensionality reduction using PCA for the latent space obtained for our G theta. From last semester, we can see that the whole latent space has actually collapsed into a very small region in the latent space. So here I have plotted a random sample from the buffer into the latent space, and the same batch of samples, when encoded using our new Sigreg regularized latent encoder, has a very spread out distribution, which means that the model is actually using all of the axes in its latent space to encode information about the visual observations. And finally, we plot out the latent trajectories by giving the model an initial latent representation and conditioning the predictor on two different tasks. One is the correct task and one is the wrong task. The correct task latent trajectory from our model is shown in blue, whereas the wrong task latent trajectory is shown in orange. And we see that the blue line is very close to the gray line being the latent trajectory obtained by encoding the ground truth visual observations. And we also observe that all of them almost start out the same, but after a while they diverge from each other, which is another observation that is consistent with what we can see in the latent imagination decodings, that the initial actions of both tasks' imaginations are the same, but then after a while they start performing different actions. The challenges faced this time is that the model actually collapses when your sig regularization is weak, where this is the standard deviation of different batches of encodings in our latent space, which starts dropping to almost 0.05 after a few hundred steps of training, which shows latent collapse. And training becomes too unstable when lambda, that is your sig regularization weight, is set too high. So as you can see, there are a lot of fluctuations happening in the sig reg loss, which then also affects the predictive loss that we saw. And finally, it is an observation that color information seems to get lost in transformer based models. Now, as future directions to this work, I aim to integrate this learned latent predictive EBM into closed loop planning and control using the proposed methodology for estimating the cost function. I also want to explore more methods to stabilize the training and further prevent latent space collapse. Since the real world is unstructured and highly stochastic, I want to explore probabilistic rollout methods to incorporate the stochasticity that's found in the real world. And finally, I want to deploy the trained pipeline I discussed above on real hardware to study how the simulation to real world transfer works. In conclusion, we saw that robot models with interpretable thoughts are trustworthy for humans. We trained a task conditioned latent predictive model which can think of how to complete a given task given a starting latent representation or starting observation. We actually visualized the model's thoughts this time using a decoder which enables transparency in these robot models. We studied the properties of the model's latent space to ensure that our regularization is working properly. So by doing all this, we have moved a step closer towards creating more trustworthy robot models. Here are some of the references, and thank you.